All right, awesome. Let's get started. Good morning. Hi, GeeCON. Thank you very much for coming. I know that in developer time, this is still very early in the morning. So thank you for being awake and coming to the conference and the talk. My name is Tomo. This is going to be the 5th How Shit Works talk, particularly at GeeCON. And today we're going to be talking about databases. So, as with every story or every journey, we got to start somewhere. We're going to start with a grumpy CEO. You have a company. You're in a company. The company presumably operates in some kind of business domain. They have a product. They want to make money. Basically, the CEO's job is to make sure there is money coming in. They don't really care that much. So they, point at you and go like, okay, well, time to go make some money. Please get started. And then you have a whole pipeline. Right? The company, as always, has a product manager, it has a chief architect, it has some management. You go through the motions, right? You start with some sort of vague product definition, you iterate. Let's assume for a second that the process works properly and everyone is fully engaged and really wants to arrive at a good outcome, which I know is woefully optimistic, but bear with me here. Right, we go through the motions, we go through the pipeline, and you end up with a concrete product definition for some product. It doesn't even matter what product it is. You manage to split it up into somewhat sane and coherent chunks of work. Your team owns a chunk, and it is your job to implement it. At this point, whatever the product is, sooner or later, almost certainly, you're going to end up with a question of which data store, which database you pick for representing whatever it is that your product deals with. Now, if you're like most of us at this point, you either have a favorite tool or you start Googling. You go on Google, you go, what are some modern databases I should have a look at? And then you run into a big problem because there are so many of them. I picked, I think, 8 examples here. There's probably more like 25 common examples of databases in use nowadays. And you need to make a choice, right? You have a product to build. You need to actually choose something and start implementing. And at this point, if you actually go on Google, you do your research, you look at these databases, you try and figure out which database to use, you're very likely going to end up like this. So, going back to the original question, which database should you choose? And the answer is, as with everything in software engineering, thank you. Problem is, it really does depend. But that's not very helpful, right? It depends on a bunch of stuff. There are a lot of different paradigms at play in databases, same as with programming languages, stacks, but even more so, especially since it's such a hot and popular topic in the last few years. NoSQLs, distributed databases, all of that stuff. There are too many options. The options are too nuanced. It's really hard sometimes to determine what is the difference between one database that you know very well and another database that seems very similar, right? What is the difference between Postgres and MySQL? It's a nuanced question. It's really hard to answer. Well, it seems, as with everything, that a little knowledge is a dangerous thing. A little knowledge can actually help you make better choices, or at least more reasoned choices. It lets you have a reasonable discussion about what products you ought to choose, how you're going to build your tech stack. And with that, we're going to be talking about how shit works databases. Now, the usual disclaimer applies. I am not an expert on databases. Far from it. Moreover, this is a humongous topic. You can cover it in any number of ways from any number of angles. You can talk about data representation on disk, distributed systems, the CAP theorem. You can talk about replication. You can talk about this from any number of angles. And we only have some 45 minutes or so, so we ended up having to pick an angle. Which also means I'm going to be simplifying a lot of things. I'm probably going to be wrong about a bunch of them. The details matter, but not in this context, in the sense that as long as you gain some kind of valid intuition about how databases work, which database you ought to pick, then I will have hopefully done my job reasonably. So take everything I say with a grain of salt, do your own research. That's always true, right? But especially in this case, because it's such a big topic. So let's start at the beginning. What is a database? We will, of course, go to the sum of human knowledge as embodied in Wikipedia. In computing, a database is an organized collection of data stored and accessed electronically. In other words, a database is the data, right? It's a collection of data. It's a bunch of data. So that's not a very useful definition. We keep on reading. Access to this data is usually provided by a database management system or DBMS. So what we're actually interested in for this topic is not so much the data, but the systems we use to control the data, store the data, query the data, et cetera, et cetera. The management systems on top of the data. Well, if that is the case, it's worth asking, what is the problem domain of a DBMS? What are the sets of problems that a database is intended to solve? Well, there's 4 major categories of problem domains that a database deals with. Data modeling, the representation of data, the schema of the data, how the data is laid out on disk, how it's stored. Data manipulation, okay? Once you have some kind of representation of data, you presumably want to actually insert data into the database, update data, delete data, whatever it is. There's data retrieval, which is what we like to call a query. And then there's a whole set of features that a DBMS typically handles that doesn't have to do with the data directly. It's things like user management, access control, security, backup, replication, all of the different things that comprise a full-blown production DBMS. Luckily for us today, we're not going to be talking about most of these things. We will focus on the 3 kind of canonical functions of a database, which is to represent data, store the data, and retrieve the data. Now, databases come in many, many, many shapes and sizes, but critically, they also differ a lot in the representation of data, right? Given a piece of data, given an entity, say a user object, right? You have the relational model, the classic SQL-based model that we all know and love. But you also have document stores like MongoDB. You have graph databases like Neo4j or whatever. Geospatial databases for purposes of geographic searches. You have time series databases, right? You have all of these different ways of representing the same piece of data. And fortunately, we don't have to cover a lot of them either, because as it turns out, most if not all of these can basically be represented on top of a key value store. Now, I'm not saying that's what you should do. I'm not saying you should pick a key value store necessarily, but it makes our job today a lot easier because we don't have to cover all of the different representations. We can just talk about key value stores in the abstract, and you can assume that everything we say about key value stores will in some way or other extend to all of these other representations. So key value stores is what we're going to be talking about largely today. Next, there is absolutely no way to avoid it. A database deals with data. The data has to be stored somewhere. Has to be stored where? Has to be stored how? Some databases operate entirely in memory. Some databases are optimized for modern storage subsystems like SSDs. And then a lot of the databases that we know and a lot of the mechanisms, the algorithms, the data structures that databases employ were actually originally designed for magnetic storage media or even tape drives, right? But whatever the case, it is the job of a database to take your data and put it somewhere and retrieve it from that somewhere. So, small digression, right? Let's think back to maybe our university days, depending on how you got started. Do you remember binary search trees? A very, 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 very simple concept. If you keep your data sorted, it is much faster to search through. It really is that simple. You have a bunch of numbers. If you store them in a tree structure, then you will be able to look up the data very efficiently. So for instance, if we look for the number 5, we don't have to go through all of the different numbers we stored in our data structure. We can, make some ahead of time compromises so that we can arrive at that data very efficiently. In the case of a binary search tree, that would be O log n, okay, logarithmic efficiency. Right. Unfortunately, not all data structures are suitable for all sorts of data storage. In our case, I chose the binary search tree because probably everyone in the audience is well familiar with them. There are, however, problems with binary search trees. They're very ill-suited. They're really, really bad for on-disk storage for two canonical reasons. One is they don't branch very far, which means you have a lot of different hops on your graph on disk, and they have pathological behaviors. So for instance, this is a perfectly valid binary search tree as well, except if you were to look for anything, you basically get linear complexity. You get O of n. So obviously, binary search trees are not a useful representation for the purposes of database. However, there are other representations that are similar enough in concept that it's worth looking into, and these are the ones we're going to be focusing on today. A database stores data on disk, fundamentally. Any database that isn't durable, that's like an in-memory database, is interesting, but it's not particularly meaningful to our discussion today. For a very simple reason. Does your data fit in memory? No. Then you probably can't use an in-memory database. Let's just leave those to the side. Let us focus our discussion on any database system that stores data durably, that is to say on disk, is intended not to lose data, and the whole point is to give you a system that can store and retrieve that data efficiently, because that ultimately is what a database is all about. So, expanding on the idea of a binary search tree, let us talk about the data structures, the sort of data structures on disk that common databases nowadays today use. And we're going to be focusing on two major data structures today, and we're going to be starting with the most common one, which is B trees. Now, a B tree is a type of balanced tree, and what is important to understand here is that any balanced tree structure basically attempts to achieve three goals, and these goals are often have to be traded off one against the other. The idea is we want to limit the tree height because every hop within the tree to do a lookup is essentially a random I/O. The idea is to limit the amount of random I/O, which in 2 decades ago meant a very, very slow disk seek. And limiting the tree height is what gets you there, right? The fewer hops you have to do on the disk, the faster your data retrieval is. But we also want to limit the cost of doing a write. So when you add a piece of data to your database, as you know, depending on how you model your data in whatever database you choose, the cost of a write is traded off against the performance of a read. There's always these two things that are working kind of one against the other, and the whole point of these data structures is to either give you better performance, limit the impact of one against the other, in this case, limit the impact of a write on the database in terms of performance, and avoid waste. You don't want to waste disk space, you don't want to waste memory, you don't want to waste CPU cycles, and you don't want to waste I/O on anything. So balanced trees turn out to be a really useful structure, and whatever research you do into databases, you are going to sooner or later run into the kind of unfortunate truth that most databases today are built on some variation of one of two major data structures. And those are the ones we're going to be covering today. So let's talk B trees. B trees are self-balancing trees. They are the data structure that most databases use for indices, right? The way indices are implemented in MySQL, Postgres, most of the databases you're familiar with are as some variation on a theme of B trees. They're actually in use for a lot of different things. So many file systems that you use today, including ext4 and BetterFS and a bunch of others, are also built on some variation of B trees. So it is an immensely useful data structure. And it is immensely useful precisely because it is designed for on-disk storage. It is designed to limit the amount of interaction between the software and the disk, okay, to minimize I/O. It is designed for fast and efficient querying of data from, retrieval of data from that data structure on disk. That is basically the purpose of a B tree. And to have some intuition about how your database works behind the scenes, let us spend hopefully no more than 5 minutes talking about how B trees actually work. Now, B tree is a tree. It's a tree structure. The difference, one of the obvious differences between a binary tree and a B tree is that a binary tree, by definition, being a binary tree, means that every node in a tree has 2 children, up to 2 children. Right? That is kind of part and parcel with the definition because it's a binary tree. B trees are a generalization of that concept. Any B tree is defined with what's called an order. And essentially, a B tree, as in this example, a B tree of order 5 is one where every node in the tree is allowed to have up to 5 children. And more importantly, B trees are designed in a way where every node in the tree can not only have up to 5 children, if the order is 5, it can also have up to 4 keys. So the way you want to look at it is basically every key that's stored in every node defines a range. Everything to the left of the key are other keys, other nodes that are less than that key. So for instance, if we have that root node, right, the top of the tree, and the first key there is 82, you have everything that is referenced left of that key, right? You have that child that is referenced from the left of the 82. Everything there is less than 82 by definition, which means that if you want to do a lookup on a key that's, say, 15, that's less than 82, you can totally eliminate all of the children in the tree that are on the right side of that 82. And that's what gives you, fundamentally, that's what gives you efficient lookups, because you can divide and conquer the graph. You can basically only follow down the graph in the direction that eliminates the most possibilities. Now, where B trees are really, really smart is that B trees are designed in a way, I guess I would say, B trees are designed to minimize the I/O required to add data and to look up data at the same time. So the whole tree structure gives us efficient lookups. The fact that nodes in a B tree can store many, many, many keys, right? 5 is just an arbitrary example. The actual B trees that are in use in databases and file systems, etc., define the number of keys that are allowed to exist in each node based on things like page size on disk, right? So they're optimized to minimize I/O on disk, and they have branching factors or order that is, easily in the hundreds, depending on what kind of database you're looking at. What is interesting in a B tree and the way that it minimizes I/O is that when you want to add a value to a B tree, say in this case we want to add the key 26 to a pre-existing B tree. We follow the tree structure, right? Less than 82, we go left. Less than 27, we go left again. Now we want to add a key to that bottom node where it computes. Now, the way a B tree works is it allows up to n-1, where n is the order, right? We have a B tree of order 5. We're allowed up to 4 keys per node. So if we were to add that 26 number to the bottom node, it would not meet that requirement, right? There's suddenly 5 keys in a node, that's not allowed, which is when B keys use splits and merges. The whole idea is this. When you have a node that has too many keys, right, which means every now and again you add a certain amount of data to your database, you cross a certain threshold. At that point, what you want to do is you want, again, with minimal I/O, you want to rearrange the structure so that it maintains those properties, so that it is still efficient to look up, and although it is efficient to look up, you don't need a lot of I/O in order to rebalance the tree. So that's called a split. There's too many keys on that bottom node. There's 5 keys instead of 4. If it's order 5, the limit is 4. And then what it does is it takes the median, okay, the middle value essentially in that node, pushes it up to the parent node. So the middle value is 13 in this case. It pushes it up 1 node, and it takes the node that has too many keys and splits it into 2 nodes. Right, so you have this, this interesting phenomenon where as you add or remove data from the B tree, the bottom nodes tend to split up and merge, depending on whether data is added or removed from the B tree, in a way that minimizes I/O, but also keeps the lookup structure very, very efficient. That is all you need to know. Okay, where there is a wealth of information about B trees. It is actually, they're pretty simple to understand conceptually and incredibly hard to build in practice because there are so many variations and so many different ways of optimizing B trees. But fundamentally, what they are is a self-balancing tree structure. And by self-balancing, what it means is that they don't get into those pathological situations like, say, a binary tree would. They always provide consistent logarithmic lookup complexity. They're designed for on-disk storage, so the fact that you don't generally have to move data around on disk except when you have a split or a merge, which is something you can actually control pretty well, right? You can define the order. You can do a lot of interesting performance benchmarks to figure out what is the most efficient on this structure for your B tree. But what it means is they minimize disk writes. Right? When you add data, generally, you don't need to do very heavy shuffling of data on disk. And that is why B trees are so useful, because random memory access is expensive, whether it's on physical memory on your machine, whether it's in RAM, certainly on magnetic media, even in SSDs. You want to minimize random I/O in all cases. And crucially, they're optimized for reads. Because of the tree structure, circling back to this, lookups are still very efficient. And that is the whole point of a B tree. Efficient lookups, amortized write cost, and convenient structure for on-disk storage. And this is why B trees are commonly used as the index structure for any database you'd care to mention that's like a traditional SQL database. Postgres uses B tree indices, MySQL uses B tree indices, SQL Server, Oracle, your favorite file system, all of these systems use B trees under the hood to provide efficient lookups and relatively cheap in terms of I/O writes. Now, this isn't always a good solution. It really depends on what it is you're trying to do. So let's pretend we're building Twitter again, right? We're working for Twitter or some other social network provider, and our team is tasked with designing the storage subsystem for likes and dislikes. When user X likes tweet Y, we want to store a record of that, and we want to be able to use that in subsequent computation, lookups, etc. Now, what's interesting here is that likes and dislikes are an extremely frequent operation. These things happen all the time. Just imagine how many times you hit like the little heart icon just today, probably on GeeCON tweets or whatever. It is really one of the most common operations people perform on social networks. So the question is, which data representation do we pick? Like, let's assume we're picking a database for this purpose. What database are we going to pick? A database based on a B tree structure? Well, you can certainly represent likes and dislikes on top of SQL Server or MySQL, right? But is that the right tool for the job? Obviously, the answer in this case is it depends. Turns out for that type of product, for that type of structure of data, B trees are not that good of a fit. Writes to B trees are costly. If we circle back a few slides and talk about how to add a key to a node, whether or not you need to split the node doesn't even matter. The first thing you need to do to add any piece of data to a B tree is you need to figure out where that piece of data should reside, which node should accept that key. And that happens even before you decide whether or not a split is necessary or a merge or any of those things. Right? First thing you do is you need to follow the tree to figure out where that 26 goes. That means for every write, every update, every insert, every deletion on a database that's built off of a B tree, the first thing you have to do is a lookup. Okay, read before write. That is potentially an expensive operation. The second thing that happens is because potentially you need to not only add the key to the node, you might need to split nodes and merge nodes and do all of this, shall we say, housekeeping that a B tree needs to do in order to remain efficient. You have what's called write amplification. Right? You added one key, right? One integer to the B tree, and you ended up with a cascade of node splits and node merges and all of these things moving around the disk. Right? All I wanted to add was 4 bytes to the index. I ended up moving, 60 kilobytes worth of blocks one way or the other. That is quite expensive, right? That is potentially a lot more expensive than the actual piece of data that I wanted to add to my B tree. So that's called write amplification. And there's also a lot of wasted space. In particular, any tree structure that is like a B tree that is designed to minimize I/O on write has to have some room to grow, right? If a node is allowed to have 5 keys, and if a node is allowed to have 4 keys and it only has 1, then I have 3 slots for keys that are just wasted space, right? So there's a lot of slack inherent in any tree structure that is designed to minimize write cost. More importantly, though, for a social network, if you can imagine what Twitter does with that information, user X like tweet Y. It's a pretty straightforward statement. Where is it in use? Well, it turns out you don't look up that actual fact very often. You want to know which users, whatever. If I am user X and I'm looking at tweet Y, I want to know that I have liked it. That's a lookup. But that doesn't really happen very often. Those facts are used not so much in lookups, but in aggregate. Right? We take that information, we run it through some sort of batch processing system in order to generate a model that we can use for, determining the scores of tweets or the scores of users on the social network. We don't actually care about the piece of data as such in and of itself. We don't look it up very often. So if we store very frequent facts, right? Users like tweets. They do that all the time. We need to store all of that information. And we use it in aggregate, but we don't actually look it up. Any optimization that the data structure does in order to guarantee efficient lookups is totally wasted. We don't actually need a data structure that provides very, very fast reads for that data, and we are paying the cost of that sort of optimization that a B tree provides, which is a cost that we are paying unnecessarily. We don't actually need it. So enter the second data structure that we're going to cover today, and that is log-structured merge trees, or what's called LSM trees. Now, B trees are a little convoluted to explain. LSM trees are actually really, really simple, especially for those of you that have at least some vague memories of your university days and remember merge sorts. Fundamentally, an LSM tree is a piece of code, a library, or whatever, that handles writes, right? It's a data store. It provides the same conceptual API as a B tree. You have a database, writes come in. The first thing that an LSM-based database does is it maintains a memory buffer. When you have a write that comes in, it is added to what's typically called a mem table. And writes are timestamped, version timestamped, whatever you prefer. right? That means that in memory, I just have a list of all the different writes that came in, and I aggregate them. I just take the write, I stick it in an array list somewhere, and I'm happy. I'm basically done with the write as far as the client is concerned. Obviously, that's not useful because it's all in memory. It's wasteful. I keep older versions of all the different writes. That is not in and of itself a very interesting data structure. What is interesting is that once I reach a certain threshold, a certain amount of writes, a certain amount of data, I want to flush that buffer to disk because I want my database to be durable, but also I want to get rid of unnecessary data in flight. So what an LSM tree does is it takes that very simple listing of writes that's kept in the memory table, it sorts it by key, and it flushes it to disk as a sorted string table, SS table. And it is exactly as simple as it sounds. You take the data you have in memory, get rid of writes. So for instance, in this case, we have 2 writes to the key that is called C, right? One write comes after the other, so it overwrites the data in that slot that was previously written. We don't really need the original value of C. We can just get rid of it. So we sort the keys, we get rid of all data, we flush that sorted table to disk as an SS table. And in terms of writes, that's it. An LSM tree, the write path for any database built on LSM trees is basically this. Stick the write in memory, at some point flush it to disk as a sorted table of keys and values along with their timestamps. Where things get interesting with an LSM tree are when you want to read, when you want to do a lookup of data. So for instance, let's say we have a database that has, some kind of list of writes that came through it. It maintains that memory table. At this point, we've already been working for a while, so we've flushed 3 different SS tables to disk. And now we need to answer what is the current value that is for the key that is B. So the first thing we do is we look at the memory table, right? The memory table is essentially the most recent set of writes to that database. So obviously, if the key exists in the memory table, that will be, and hasn't been flushed to disk yet, that will be the most recent value of B. If we can't find it in the memory table, then we need to actually start looking through all of the existing SS tables on disk. Why all of them? Because nothing guarantees that the key, that the requisite key, B in this case, even exists in any of them. Right? Writes come in any arbitrary order. They are flushed to disk in any order. There is nothing to guarantee that key B will exist in SS table 2 or SS table 3 or even SS table 1. So we need to look at all of them. And what we essentially do is the same thing as a merge sort. We look at all of these tables. We do a lookup. Because they're sorted, lookups are relatively efficient within a table. It's a binary search within a table. Right? So we look for the key B in SS table 1, in SS table 2, in SS table 3. We pick the value with the latest timestamp, and that is the value of the lookup, right? In this case, B exists in all 3 flush tables on disk, but the most recent value is 3. That is the result of the lookup. Now, looking at this, you probably noticed some issues. First of all, the least of the issues is that old versions of B in this case are retained. Right? I have a structure on disk that has old versions, ostensibly useless old versions of whatever it is represented by the key B, and that is incredibly wasteful. It's useful if I am interested in kind of the history of the values belonging to that key, but it is wasteful in space. Much more importantly, though, I need to actually query every single SS table stored on disk, which means that the I/O cost of a lookup is, in a sense, proportional to the age of a database. The more SS tables I have flushed to disk, the more lookups I need to do on top of those SS tables on disk. Now, there are several ways of dealing with that cost. The simplest of them is to say, if I have a whole bunch of SS tables on disk, I can maintain a much simpler structure next to each of them that tells me which keys are present in that SS table. Right? If I have for each SS table the set of keys that exist in that SS table, and for instance, I do a lookup on, I don't know, key O, for instance, which only exists on one of them, I can look at every single SS table and just skip the lookup completely if the key doesn't exist in there. And Bloom filters, which is a pretty interesting probabilistic data structure that you can look into, but is way outside the scope of this talk, is often used exactly for that purpose. Most actual implementations of LSM trees maintain a key set next to each SS table in order to completely avoid lookups. But that's still not good enough because we're still accruing more and more and more SS tables on disk. Right? So the more SS tables we have, the more expensive a lookup becomes because we have to do those sub-lookups in each SS table. So obviously that is not a tenable solution in and of itself. Where LSM trees get useful and interesting and similar to merge sort is through a process called compaction. Now you will notice, because essentially this is an append-only data structure, right? We take in data, we flush a new SS table to disk. We never touch that table again, right? That SS table remains as it is, an immutable data structure on disk until the end of time. What it does mean, though, is that we can take a bunch of SS tables and merge them together with essentially a merge sort. It is a very cheap operation. You linearly, because they're sorted, you can just maintain pointers on the SS tables and kind of go in lockstep and produce from a bunch of SS tables one bigger SS table that represents the same data with the same timestamps. Right? So we take these 4 example SS tables, we merge them into one larger SS table, and we can just use that instead of looking up on top of all of those 4 because the data is immutable. So what LSM trees actually do is they have typically some sort of scheduler that looks, based on certain triggers, whether it's time, whether it's size of data. It determines when it is opportunistically useful to take a bunch of SS tables and merge them into one bigger one. And typically what actual implementations do is they maintain kind of a hierarchy of exponentially larger SS tables. Right? Whenever you have a certain amount of data, you merge a bunch of SS tables into a bigger one. You call it, you push it down to a lower level, and then you only need to do a capped number of lookups. You can actually determine ahead of time how many SS tables are you gonna have to do a lookup on in order to provide a full-blown across the whole database lookup. And it turns out that this is a really, really, really useful approach to things because it is optimized for writes, not reads. It doesn't mean reads are slow. In the same way that writes to a B tree don't have to be slow, and there are a lot of iterations and variations and optimizations you can do on top of both of these data structures, but LSM trees are fundamentally very, very suitable to high write volumes. When you have any sort of data that comes in at a very high frequency, but isn't looked up as often, so lookups don't have to be slow, but they're not as efficient as with a B tree because the data structure is not designed for that. It turns out that LSM trees are a really, really useful data structure to have, which is why a lot of sort of modern write-heavy databases use them. Cassandra, for instance, is strictly built on LSM trees. Now, Cassandra is a very interesting database for a lot of reasons, but specifically, Cassandra was initially designed exactly for this purpose, to cope with an incredibly write-heavy load. Right? Back when web scale was still a thing, still a word people used, what they generally meant is you have a lot of write-heavy traffic, a lot of events coming in, but relatively infrequent lookups. And a B tree is just not the right structure for it, which is why databases like Cassandra, RocksDB, LevelDB, WiredTiger, which is the underlying storage engine behind MongoDB, CockroachDB, a lot of the modern web scale databases use LSM trees exactly for this purpose, because they can use it to provide efficient, though not optimal, lookups, which is perfectly fine for a lot of use cases. But more importantly, the write path doesn't require any lookup ahead of time. It's totally append only. There is no write amplification because you don't need to shuffle anything. The compaction step does have some cost to it, but you can actually control that very effectively because it's a separate process. You can do compaction concurrently with everything else because the SS tables are immutable. So once you're done with compaction, you took 4 SS tables, merged them into one. At that point, you can stop looking at those 4 SS tables and throw them away or whatever it is you want to do. But up until that point, the same SS tables can still be used for lookups. So it is something you can control very well. You can do concurrently. There's no write amplification. There's no lookup. You don't need to look anything up before you add data to the structure. So it is actually a data structure that is very, very efficient for heavy write loads, like dealing with likes. So just with these 2 data structures, hopefully you're starting to get some idea of how some databases differ from one another. Okay? And it is worth noting, virtually every database that you've heard of, whether it's commercial, whether it's open source, whether it's NoSQL or SQL, whether it's a document store or a key value store or a relational database, pretty much every database you know is built on some variation of one or both of these data structures. There are interesting variations. There are different ways of combining these data structures. It's a huge topic that I'm very far from qualified to talk about effectively, but the point is every database you know ends up being built on one of these 2 data structures, which brings us back to the question, how do you choose? Now, there is no easy answer here. You can't really know everything that's out there. There are still differences between databases, even when they're built on top of the same data structures. No easy answers. But if there are a few generalized takeaways that you can take from this, they are this. First of all, depending on what it is you're doing, for the most part, hate to say this, it doesn't matter which database you pick, because whatever it is you're building probably doesn't start off at scale. It probably doesn't start off with a high degree of complexity. Push comes to shove, whatever it is you're building, unless you know exactly what it is that's going to be challenging for your particular product, you can probably implement equally on top of MySQL, or on top of Cassandra, or on top of any MongoDB, any NoSQL database you choose. They're probably all going to work. So my recommendation is, right out the gate, choose the thing you're comfortable with. If you already have work as an organization, as a person, as a team, if you already have working knowledge of any of these databases, if you're comfortable, say, with MongoDB, then just pick MongoDB, because by the time you understand your requirements enough to make a reasoned choice, you're going to have to rebuild parts of your system anyway. So start with whatever it is you know and you're comfortable with. When you actually do have meaningful choices to make, you should base your choices on these 3 things in that order. Your operational needs, right? The cost of owning and operating a database has a lot less to do with your data representation or the way you model your data or your transactionality or any of these things. The reality of it is your choice of database depends primarily on your operational capacity as an organization. Do you have ops people that can actually operate some kind of cluster database effectively. Maybe you're taking an off-the-shelf, software as a service provider like MongoDB Compass or whatever. So your operational capacity within the company is probably going to determine your choice a hell of a lot more than the product you're actually building. So that's the thing you need to look at first. The second thing you need to look at are your access patterns. The more you understand what your product actually does, what are the use cases it purports to solve, as with the social network example, right? Social networks are easy to talk about because we all know social networks and have been using them for decades. So we kind of know what to expect, right? The fact of the matter is, when you like a post, you know that that actual like as a discrete event doesn't matter much. It matters in aggregate. So if you have an understanding of your problem domain, you can actually make those determinations. This is the data I have. This is the way I'm going to be using it. These are my access patterns. Then you can start making reasoned decisions. If you know your access pattern is write heavy, that should give you some idea of which kinds of databases you want to pick. If you don't really have that many writes, but you want super efficient lookups, well, you probably want some sort of B-tree index-based database. Then again, if you're just dumping data and then doing some sort of batch processing on it, an LSM tree database might be a lot more useful to you. So your access pattern is the second thing you should be looking at. The last thing you should be looking at is scale, because the reality of it is, unless you know exactly what you're doing ahead of time, you don't really need scale. You're going to understand your scalability needs a lot better when your product actually has real users and real data and real product requirements. At that point, you can actually reason about it and go, okay, these are the things I need, therefore these categories of databases are more suitable. Of course, maybe you have some sort of hard requirement from your database, like for instance, I don't know, if you're storing metrics, you already know that you should probably pick a time series database for that, but those are kind of unusual. Like if you have a requirement that cuts off a whole portion of the available databases and makes a lot of them useless to you, then obviously you should pick something that fits your product requirements. But for the most part, when you start off on a new system, or when you're building a system that has moderate to low scale, which realistically most of us, 99% of our job is either totally unknown or very well known and low key, it's a small amount of data. In that case, just pick the thing you're most comfortable with. The fact is, almost all of the products that I've mentioned in this talk are full-blown production grade, and you can use them to build just about any product you'd care to mention. But the more you understand how these products work under the hood and what problems they aim to solve and how they solve those problems, the greater your leverage. When you're actually building a system at scale, when you actually understand your problem domain and know what kind of access patterns you have, then you can really make a reasoned decision, right? When you actually know that you have a lot of data coming in, now you have, I hope, some intuition about why, for instance, Cassandra is an interesting choice for your system. On the other hand, push comes to shove, all of these databases will probably solve your problem. But the more you know, the better you can pick. And with that, if there are any questions, I'd be happy to take them. So let's switch to Slido, which doesn't appear to work. Thank you. Okay, now I'm going to have to move somewhere so I can actually see. At some point, you know that you need to make the switch. Any idea how to convince business that this is the time to grow and it is not a technical debt? That really depends on the sort of business you run. it has been my limited experience that the point at which you need to really take your completely willy-nilly, oh, we just built it on MySQL because that's what we had, and need to make a reasoned choice, typically no one treats it as an issue of technical debt. At that point, you know that you either have a serious scalability issue, or you are going to have an influx of users, or some sort of major event in the life cycle of your company is going to happen and will require some kind of re-architecture. So how do you know that? There is no one answer, unfortunately. But yeah, typically you know. Like if you hit a scalability wall, you know. If you're gonna have 10 times as many users coming in because of some kind of marketing event, you know. At that point, you can make a reasoned decision. As for how do you know that you're at the decision point, that really depends on your company and your domain. What makes LSM a tree? That is a fair question. Dominantly, the fact that you maintain, for practical reasons, right? Any practical LSM implementation will maintain a hierarchy of sized SS tables. Right, that merge, that compaction process that we talked about earlier, you typically want to do it in exponentially increasing sizes, because that's where you actually get useful leverage out of it. So you maintain a tree of different sizes of SS tables, different practical sizes for lookups. That is probably not a very good answer, but I suspect the academic answer is one I'm not really qualified to give. Google it. It'll hopefully give you all the information you need. I think we're out of time and out of questions. Thank you very much. Enjoy the conference. If there are anything you want to discuss, I will be here outside. Thank you.